Okay, I'm giving my presentation on the name reaction Fischer esterification. So this is the basic scheme of this reaction. You have a carboxylic acid and you react it with an alcohol in a acidic solution to get an ester. So it's a very simple reaction that Fischer came up with. So Hermann Emil Fischer was a German chemist. He lived from 1852 to 1919, and he won an award for the Nobel Prize in Chemistry for his work in sugars and purines in 1902. He originally started working with his family lumber business that his father wanted him to go into, but he was really bad at business, and so much so that his father let him leave that and go pursue his real interest in science. So he went to the University of Bonn in Germany to study chemistry and physics, but then left that to go to a university in France, the University of Strasbourg, to study under a more experimentally oriented scientist, where he got his doctorate and then worked at 5 other universities in Germany after that as a professor and researcher, primarily a researcher. Fischer projections, which we all learned about with a way to draw structures of compounds, he came up with that in his work also. One of the things he's most famous for is the discovery of phenylhydrazine, which he used to characterize sugars in his research. He also discovered a family of bases, the purines, which is a very important thing. Purines are related to caffeine and theobromine, so that was a very foundational discovery that he made. And he also did a lot of work with molecular structures, so with sugars and proteins, including enzymes. He looked at the stereochemistry of all of the known sugars at the time, and also predicted all the possible isomers resulting from sugars. With the proteins and enzymes, he discovered peptide bonds and was able to synthesize artificial proteins based on that reaction, and also identified 3 amino acids. And his work, of course, led him to this esterification reaction that I'm going to be explaining now. So you start with a carboxylic acid, and then you have the alcohol and an acid catalyst, and it's a reflux reaction. So you have the reflux condenser, which you can see in this picture. Can you see the picture?
Mm-hmm.
Yes. Very cool. So the mechanism for this is, it's really simple. It's more simple than most esterification mechanisms, which is why he came up with this as a easier way to synthesize esters. So you start off with the carboxylic acid. Oh, that's not going to work very well. And you have that with, react that with the acid. So the lone pairs on the oxygen will go and attach to the hydrogen, breaking this bond and breaking that off. So then you'll have the then you'll have a positive charge on the oxygen there. So you're protonating the carboxylic acid. Can you see this? Is it too light? Okay. Cool. So then this protonated carboxylic acid has resonance structures because of the because it's protonated, because there's a slight positive charge on this oxygen atom. So that can I'm gonna draw this here. This lone pair here, well, this pi bond can break and the electrons transfer up here to this oxygen, which leads to a carbocation here with a positive charge on the carbon. And that helps to stabilize the atom. So once you have the carbocation, then you're able to react that with the oxygen, not the oxygen, the alcohol. So you have the alcohol, and I'm gonna sit down so I can write on this better. So then you have the alcohol attaching here. Well, we're just gonna draw the alcohol, and it's attacking the carbon, which bad markers, which forms a tetrahedral compound. That's not going to work at all. Here, can you pause it for a second? Okay, so here we have the alcohol, which attacked the carbon and formed the tetrahedral compound. So then the base comes. Are you kidding? This is like 2. And the negative, or the lone pairs here attached to this hydrogen here. So then this bond breaks off and the electrons go to the oxygen, forming... Okay, this is going to be too hard to see with these markers, so we're going to change things up, and I'm just going to show you on here. So that was this, the electrons, the lone pair on this base attaching to this hydrogen from the alcohol, and then that bond is breaking, and those electrons are going to the oxygen, which stabilizes it. So then you have this stabilized form. So then you add another acid, and the hydroxyl group, it doesn't matter, it could be either hydroxyl group, but one of the hydroxyl groups, the lone pair on the oxygen, will attack the hydrogen, and that will result in this compound, which has an H2O group, a water group over here. And so that's a very good leaving group, H2O, and so in the next step we see that it does leave the bond that holds the oxygen to the carbon breaks off, and the electrons go there, forming H2O. And to prevent this carbon from being positively charged and forming a carbocation, the lone pair from this oxygen, the other hydroxyl group, will form a double bond to the carbon, as seen here, so that the positive charge is on the oxygen instead of on the carbon. So then we see that, well, it's in resonance. It can go back and forth to stabilize it. So the base attacks this hydrogen and deprotonates it when it's in the this form, not the carbocation, but this form. So it deprotonates it with the hydrogen, and the bond the electrons from that bond go to the oxygen and stabilize it, forming the ester. So it sounds a little complex with all of the little steps in the mechanism, but it's really a very simple reaction and the most simplistic form of esterification that has been synthesized and created as of right now. So there's my references slide. Thank you.